Well, happy Friday. It's Friday today, and we are finally doing our section 10.3, Arcs of a Circle. And when you finish this, I'll be back on Monday, and we can answer any questions if you've had questions along the way or any trouble with homework. Hopefully you have found the homework answer keys. Well, hopefully I posted them on Google Calendar or possibly Google Classroom. They're not there yet, but hopefully I remembered to put them there. So today we're going to talk about arcs of a circle, section 10.3 in the book. Our objectives are to identify the different types of arcs, determine the measure of an arc, recognize congruent arcs, and apply the relationships between congruent arcs, chords, and central angles. Okay, so first, here we go. We're going to start with a warm-up. Go ahead and give this a shot. It should be on your notes sheet. So give that a start, and then we'll go over it. I'll go over it together with you, and you'll see if you got the right answer. Okay, so you're given circle O. You've got AB is equal to 15 minus x, and CQ is equal to 2x minus 5. So AB is this section right here. This is 15 minus x, and CQ is right here, 2x minus 5. All right. Okay, my pen was a little too thick there. We should be good to go here. We're also given OP and OQ are congruent, and they both have a measure of 2. So we're going to go ahead and mark our picture. So what do we know? If OP is congruent to OQ, these are both segments that are going to be the distance to those respective chords. So if those distances are both congruent, then we know that the chords have to be congruent. And we also know that the chords are bisected if we've got these right angles here. Okay, so how can we start to solve for CD and for our radius? Okay, so if we start by saying, well, 15 minus x has to equal the other chord, but the other chord, I don't have the whole thing, I only have segment CQ. Well, if that segment is bisected, then I know I have 2 of these. This is also 2x minus 5. So I can write my equation like 2 times 2x minus 5. And go ahead and solve for x. Adding an x to both sides, I have 5x. And adding a 10 to both sides, I have 25. So x is equal to 5. But that's not quite what we're looking for. We need to find CD. If I plug that 5 in for the x up here, all right, I get 2 times 5, which is 10. 10 minus 5 is 5. So this section, or that segment right there, is 5. This segment would be 5 here. And then this whole segment here would be 10. So CD would equal 10. And now I'm trying to find the radius. So remember, a radius is anywhere from the center out to the edge of the circle, to the circumference of the circle, or the perimeter of the circle. So if I draw in my, let me get another color here. Let's go pink. If I draw in my radius, that's what I'm trying to find. You see that I have this right triangle. And one leg here is 2, one leg is 5. So I'm going to say, well, 2 squared plus 5 squared is equal to, let's call it C squared. All right, so 4 plus 25 is 29. C is going to be the square root of 29. Well, how'd you do? Is that what you got? I guess we'll find out soon. All right, so let's start with the lesson. 10.3, arcs of a circle. What is an arc? I tried to save myself some time by just typing in our definitions here. So let's go with red. An arc consists of 2 points on a circle, and all points on the circle needed to connect the points by a single path. So if I'm talking about these points, A and B, all the points needed to connect the points by a single path. So all these points along here, okay? All those make up an arc. It's basically a piece or a portion of a circle. So this is my arc. I can write. Okay? Then we have arc center. Oh, now my little arc went away. So the arc center, the center of an arc is the center of the circle of which the arc is part of. Okay, so if this is my arc again here, between A and B, that's my arc. Oops. Then this is the arc's center here at O. The center of the circle of which the arc is a part. If I just drew down here a center and this out here from here to here, this would be my arc and this would be my center, arc center. Next we have central angle, an angle whose vertex is at the center of a circle. So this here is our center. Again, we have the arc here. Oops. An angle whose vertex is at the center. So this central angle, here's my angle. And this is the vertex here at O, and notice that is the center of my circle. So that, because it kind of makes sense, right? It's an angle that comes from the center of the circle. So that is a central angle. Notice how the radii, OA, this is a radius right here, and OB, determine the central angle, angle AOB. Now let's talk about these different kinds of arcs. We have a minor arc, a major arc, and a semicircle. So a minor arc is going to be less than 180. You know, if you go all the way around the whole entire circle, from point A all the way back to point A again, it's 360 degrees. So if you go less than 180 degrees, it's going to be a minor arc. Let me see if I can erase this. No? How do I erase? Oops. There we go. So a minor arc, I could call arc AB. Why isn't this writing? Let's see. I'm having trouble here. Okay. It's not writing. There we go. If I'm talking just about arc AB, that would be a minor arc because it's less than 180. What happened to my O? Okay. Less than 180 degrees. Okay. And how do I write that? The notation for a minor arc uses 2 letters. So I would write arc AB. The arc notation is this arc above the AB, the letters AB. All right, we also have a major arc. For our major arc, we need to go greater than 180 degrees. So if I see on this circle here, if I wanted to go all the way around from A to B, but I wanted to go the long way, if I went all the way from A through C all the way around to B, that would be called a major arc. So it's greater than 180 degrees, its notation uses 3 letters, okay, and it would be called, in this case, arc ACB, okay. The way I think of this is it starts at A, it goes through C all the way around to B. Okay, so this is where we're just talking about the arc. If we want to talk about the actual measure of the arc, we call that the measure of arc ACB. A little M in front tells me I need the actual measurement, like the angle measurement. And when we don't have that M in front, we're just talking about that arc. So likewise up here I could say the measure of arc AB. Okay, we'll talk about that more a little bit later. All right, now when we're talking about the semicircle, okay, makes kind of sense. Semicircle, it's a half a circle. It's going to equal 180 degrees. Okay, so if I drew in a diameter here, okay, let me draw in the diameter, and let's just call it x, y. Okay, so if I have diameter x, y, and I'm talking about the semicircle, that arc, I would label it x, y, but I could also label it x, a, y. In this case, for the semicircle, it really doesn't matter if you use 2 letters or 3 letters, because either direction you go, whether you go through A and B to Y, or you go around the other way through C to Y, it's still going to be 180 degrees. Okay. Okay, now on your sheet we have example 1. You're to find the measure of the major arc ACB. So that means it starts at A, it goes through C all the way around to B. What is the measure of that arc? Go ahead and answer that. Okay, in order to find the measure of arc ACB, we know that all the way around the whole entire circle is 360 degrees. So if I start with 360 degrees and I subtract out this smaller arc here, the 20 degrees, I'll get the measure of what was left over for this major arc here. Okay, so I get 340 degrees. Our next example, go ahead and try this one. Find the measure of the major arc XDY. Okay, so in order to find the measure of arc XDY, measure of arc XDY, if I know this central angle here is 110 degrees, then I know that the arc measure is also 110 degrees. And if that's 110 degrees, I'm looking for the major arc X through D to Y. So again, I'm going to take 360 and subtract that 110, which gives me 250 degrees. So we have 2 ways to talk about arc. We have arc length, which is a distance, and we have the arc angle, which is related to the angle measure, the central angle measure. Okay, so if we're talking about arc length, we're talking about the distance. How long is it? If I took a piece of string and measured it from, say, D to E, how long would that piece of string be? So how long is it? Okay, notice if let's see if I can just kind of hand draw another circle in here. Well, it's supposed to be a good circle with the center O. and I had a point out here, D and E. Does it look like that arc, and say I'm connecting here, so they both come from the same angle measure. Do you think this arc length from, let's call this D prime and E prime, do you think this arc length is the same as this arc length here? So DE, arc length DE congruent to arc length D prime E prime? Well, you can kind of see. I mean, imagine the string, holding a string and measuring this one and then measuring this one. Don't you think the string on this outside one is going to be longer? True, it's going to be longer. So arc length is like your string measurement. We're going to be, right now, we're going to be talking mostly about the arc angle measure, or we call it arc measure. Oops, arc measure. It's a part of the circle's angle sum. So it's part of the circle's angle sum. So if I'm looking at this example here again, and this is my central angle here, DOE, then this arc measure of DE is going to be congruent to the arc measure of D prime E prime. So let's just say that this is 90. Then this arc measure here would be 90, and this would be 90 here. So the arc measure is going to be congruent there. Again, we're going to focus on the arc angle measure right now. Okay, so let's try some problems here. You're going to determine the arc measure here. I'll give you a second to kind of think about that. You can pause here if you want. Okay, if I'm looking for the measure of arc CE, so CE, arc CE is this right here. Okay, I'm looking for that arc measure. Well, it's gonna be a combination of this measurement from C to D and D to E. So we're going to add 53 plus 34, and we get 87 degrees. If we're looking at EF, let me just change colors here. Let's go green. If I'm looking for the measure of EF, well, nothing's written there, but how can I find it out? Well, I know here that this chord, CF, goes through the center. So this is the diameter, making this from C all the way through to F a semicircle. So I know the whole thing adds up to 180. And this part here is 34 and 53. Then I know that this remaining part here has to be 180 minus 87. Okay, it's minus the 53 and the 34. So that gives us 93. The measure of ECK. So ECK is a major arc. It's going to go purple here. ECK. So I start at E, I go through C, oops, E, and I go through C all the way to K. So I'm looking at this arc here. Okay, I know that this is 34 here, this is 53, and then I don't know any of the measures here. But in this half circle here, that's 180, I know that these three pieces of the arcs are congruent. So if I take 180 and I divide by 3, then I know each one of these is 60. So basically I'm going to add up 34, 53, 60, and 60, and I'm going to get 207. And then DFC. What color can I choose now? Let's go some kind of blue. Okay, DFC, that means I'm starting at D, going through F, whoops, what's happening there? D, going through F, hold on. What's happening? It's not writing for me. I'm starting at D and I'm going through F all the way around to C. Wow, that goes most of the circle there. D all the way through F, all around to C. This part here is the only part that's not included. So I can just say 360 minus 53. That'll give me all the rest. So that's going to be 307 degrees. So arcs are really nice. Everything deals with 360. So we'll see how we do with that. Okay, moving on to the next. I've got a whole bunch of theorems. Now you don't have to write them down. I'm just going to kind of read through them and try to describe what it is they're talking about. If we have two central angles of a circle, or congruent circles, and we know that those are congruent. So let's draw in two central angles. Okay, I'll draw it here and here, and let's just say those two central angles are congruent. Then I know that their intercepted arcs are congruent. They're intercepted arcs. That means this part here is congruent to this part here. Those two arcs have to be congruent. Okay, so let's see if I can erase and it works. Now, number 2 says if two arcs of a circle or congruent circles are congruent, then their corresponding central angles are congruent. Oh boy. Well, that just says the converse of what I just talked about. That's saying if these two arcs are congruent, then we know their central angles are congruent. That makes sense. Now, if two central angles of a circle, I should just leave these up, huh? If two central angles of a circle are congruent, then their corresponding chords are congruent. So let's draw in this chord. We've got a chord from here to here, and we've got a chord from here to here. If these two angles are congruent, then the two chords are going to be congruent. And now let's just look ahead to the next one. If two chords of a circle are congruent, then their corresponding angles are congruent. So this is just the converse. I've got these two chords are congruent, then I know that these angles are congruent. And if two arcs of a circle are congruent, then the corresponding chords are congruent. So let me grab another color here. If I know now that these two arcs are congruent, then I know the chords are congruent. Okay, and then we have the converse of that one. If two chords of a circle are congruent, then the corresponding arcs are congruent. So putting all those together, basically, I've got this statement at the bottom that kind of sums it up. If we have congruent chords, we know we have congruent arcs, and then we know we have the congruent central angles. Okay, they go back and forth. Okay, I'm going to try to go quickly through these proofs because it's Wednesday and it's almost 3 o'clock and the bell is going to ring and I want to get through these without having too much commotion out in the halls. So here we're given that we've got circle B and we know that D is the midpoint of AC. So if D is the midpoint of arc AC, it works the same way as midpoint works. We would have AD is congruent to DC. Okay, that's what the midpoint means. And I'm trying to prove that BD bisects angle ABC. So I'm going to start with my given. I have circle B, and I know that D is the midpoint of AC. Okay, that's given. All right, next I can say that arc AD, this is the part I already kind of marked on the picture, arc AD is congruent to arc DC. There we go. And why is that? Well, the midpoint of an arc divides the arc into two congruent arcs. Midpoint divides the arc into two congruent arcs. All right, so because of our theorem we just learned, if those two arcs are congruent, then we know that their central angles are congruent. So here I can say that angle ABD is congruent to angle DBC. Okay, if two arcs are congruent, then the corresponding central angles are congruent. I'm just going to say then angles are congruent. You know that this means central angles. Okay, so how do I mark that? Well, I'm going to mark this angle congruent to that angle. And knowing that, then I can say, well, BD bisects angle ABC. And just put this into words then. We know if a ray divides an angle into two congruent angles, then the ray bisects the angle. Okay, I went ahead and wrote it out so that you would have it there. Okay, so that finishes that proof. Not too bad, 4 steps. Okay, so now our last proof. We're given that circle P and circle Q are our names of our circles. We have angle P congruent to angle Q. Okay, angle P congruent to angle Q. And we're given that AR is congruent to RD. So AR is congruent to RD. We're trying to prove that AB, arc AB, is congruent to arc CD. So this is a little bit more involved. Just a little bit more to write, I think. We're going to start with our given. We've got circle P and circle Q. Can't write with this. Okay. That's going to be our given. And we've also got angle P congruent to angle Q given. Okay, now, what can we get from that? Well, if we have these two angles, P and Q are congruent, then look at this triangle, PRQ. That would make that an isosceles triangle. So if it's an isosceles triangle, then we know that RP is congruent to RQ. RP is congruent to RQ. Okay, so if we've got these two angles of a triangle congruent, then I know that I've got these two sides congruent. Next, we're going to use our next given, that AR is congruent to RD. AR congruent to RD. Why isn't it writing there? RD. That was our given. And then from that, if AR is congruent to RD and we know PR is congruent to RQ, then by using the subtraction property, I can subtract AR from PR and get that AP is congruent to DQ. So AP congruent to DQ. Subtraction. And really, subtraction, and I'll just list, it's from 3 and 4. We're subtracting those two pieces. Our next step, then, we can go ahead and say that circle P is congruent to circle Q. Circle P congruent to circle Q. And that's because once we got AP congruent to DQ, those are actually the radii in those two triangles. So if we have congruent radii, then we have congruent circles. So circles with congruent radii are congruent. And if we know that those two angles, those angle P and angle Q, are going to be central angles because P and Q are the centers of those circles, if those two angles are congruent, then we know those two arcs are congruent. So arc AB is congruent to arc CD. So if two central angles of congruent circles are congruent, then their intercepted arcs are congruent. And there we go. So now that finishes up this lesson, and you can start the homework, which you will find in Google Calendar or use your book. Here we go. All right, you guys have a great weekend. I will see you on Monday.